Hello, everyone. Welcome to what is probably the final champ talk of the school year. I can't believe it. But I am very pleased, as always, to introduce Vinh Nguyen from Purdue, who will tell us about Lech's inequality for generalized multiplicities. Vinh.
Okay, I want to first thank the organizers for allowing me this opportunity to speak. And I also want to thank everyone for coming and also, I guess, for watching later as well. Okay, so the work in this presentation is joint work with Kelsey Walters. And throughout this talk, all rings are Noetherian and modules are finitely generated. Okay, I just want to establish some notation first. So R usually denotes a Noetherian local ring, M is its maximal ideal, and K is its residue theorem. We're also going to keep things simple by assuming that K is infinite. Now, the residue field being infinite is not really much of an assumption because we can do the standard technique by passing from R to R join X and then localize at the extension of the maximal ideal. Now, a lot of the invariants in my talk, such as the dimension, and multiplicity, and colength, stays the same when we pass to this other ring. Okay, I just want to first review the Hilbert-Samuel multiplicity. So when I is M primary, its colength is going to be finite, and the colength of all of the powers of the ideal will also be finite. So we can study this length function, and it turns out that when the power is large, this length function behaves as a polynomial in degree d. So we can pick out its leading coefficient by passing to this limit, and this integer is called the multiplicity of I. Okay, so E of R does not denote the multiplicity of the unit ideal, but instead denotes the multiplicity of the maximal ideal. And we're going to call this the multiplicity of the ring. So I'm just also going to throw this fact in here because I'm going to use it later during calculations. But the multiplicity of the kth power of an ideal is equal to k to the d times the multiplicity of the ideal. So multiplicity have various applications, one of which is that it detects integral dependence. And there's this well-known criterion by Ries that says that when you have two ideals, J sitting inside I, that are both M primary, then their integral closure are the same if and only if their multiplicity is the same. Okay, also the multiplicities of rings in some sense measures how bad the singularity of the ring is. So for instance, here are a couple of results. For some of these results, we're going to have to assume that R is formally equidimensional. So the first result is a famous theorem by Nagata, and he was able to characterize regularity of rings based on the fact that if the multiplicity of the ring is equal to 1. I also want to point out that 1 is in fact the colength of the maximal ideal. Okay, so recently Macaulay and Smirnov generalized this result by characterizing regularity based on if the multiplicity of integrally closed ideal agrees with the colength of these ideals. So of course, the maximal ideal is integrally closed. So they recover the Gauss theorem. Okay, so there's another well-known result, which is a characterization of Cohen-Macaulayness. And so a ring is Cohen-Macaulay if and only if the multiplicity of parameter ideals equals its colength. So also, while we're in a Cohen-Macaulay case, we can also characterize whether or not I is a complete intersection based on, again, the equality of multiplicity and colength. Okay, so R is called Buchsbaum if and only if the difference between multiplicity and colength is constant for any parameter ideal. And then finally, even more general type of ring than Buchsbaum is called generalized Cohen-Macaulay. And so R is generalized Cohen-Macaulay if and only if the set of all differences between multiplicity and colength for parameter ideals is bounded above. Okay, so there's various ways to generalize Hilbert-Samuel multiplicity. One way is to measure the colength of multiple M primary ideals at the same time. So we're going to take a look at this length function here of the powers of the ideals. And this will behave as a polynomial in multiple variables when n1 to nr is large. So now we have a whole family of leading coefficient, and we can look at a particular leading term by picking these positive integers a1 to ar to add up to d. And so we're going to look at the monomial term that corresponds to this choice of a1 to ar. So again, we can normalize this leading coefficient, and we get a certain type of mixed multiplicities for our ideals. And unfortunately, because our polynomial is in multiple variables, there's no way to define this multiplicity as a limit, because you can't pick out the leading terms as a limit. Okay, so here's some alternative notation that I'll use throughout the talk. So we can list out each of the ideals a certain amount of times based on the A's. And notice that there will be a total of d many ideals inside the multiplicity notation. So if we do not want to distinguish the ideals, we can just say E of I1 to ID. Okay, so we obviously recovered the Hilbert-Samuel multiplicity when R equals 1. So in that case, there's only one ideal. But also a little bit less non-trivially, when R is bigger than 1, we can just look at a single ideal and pick the leading term that corresponds to that ideal. So we're going to pick A1 equal to D, and A2 to AR equal to 0. So we get the mixed multiplicity of this certain type. And using the alternative notation, this is the multiplicity of I1 written out d many times. And this is in fact going to be equal to the Hilbert-Samuel multiplicity of I1. So to see this, let's look at this length function. And we're going to fix n to the nr. Now, when n1 is large, the term that involves x1 to d dominates. And we can view this length function as a polynomial in only one variable, x1. And in fact, it's going to agree with the Hilbert polynomial for I1 up to a certain constant. Okay, so another way to generalize Hilbert-Samuel multiplicity is to do it for modules. So the question now is, can we replace the ideal with a module? So we're going to begin with a submodule or free module. And so we have to come up with a notion of powers of a module. Okay, so to do so, let's look at the induced map between the symmetric algebra M to the symmetric algebra F. And just note that the symmetric algebra F is a polynomial ring in little r many variables over big R. So the image of the symmetric algebra M is called the Riesz algebra of M. And we can define the powers of M as the nth degree component of the Riesz algebra. Okay, so if the colength of M inside F is finite, and then so will the colength of all the powers of M inside the powers of F. So again, we can look at this length function and study it when n is large. And Buchsbaum-Rim proved that when n is large, this length function behaves as a polynomial. And again, we can pick out the leading coefficient of this polynomial, and this defines the Buchsbaum-Rim multiplicity of M. Okay, when R is 1, then M can be viewed as an ideal in the ring, and the powers of M are exactly the powers of M as an ideal. So the Buchsbaum-Rim multiplicity is the Hilbert-Samuel multiplicity of M as an ideal. Okay, so let's look at this special case where M is a direct sum of ideals. So in this case, we can talk about the mixed multiplicity of the ideals and the Buchsbaum-Rim multiplicity of M. And it turns out there's a beautiful formula that relates to two multiplicities. So let's analyze the quotient of the powers of F by the powers of M. It turns out this is isomorphic to the direct sum of the quotient by the different powers of I. And so you can expect that the Buchsbaum-Rim multiplicity, which is the thing that is related to the left-hand side, is equal to the mixed multiplicity, which is the thing that's related to the length of the right-hand side. So it turns out that Buchsbaum-Rim multiplicity is the sum of all of the mixed multiplicity of the ideals. And this formula will be used later. Okay, so I just want to make some quick mention, which are further generalizations. And my talk isn't really concerned with these generalizations, so I'm not going to go into too much details about it, but I just want to mention them. So one generalization is is called the epsilon multiplicity, and this is for ideals that are not necessary and primary. So we can force the quotient by the powers of the ideal to have finite length by passing to the zeroth local cohomology. And so we can measure the length of the zeroth local cohomology of the powers of I instead. So it turns out that this length function doesn't necessarily have polynomial behavior, but it is bounded above by a function that is a polynomial. So we can pass to the lim sup instead and define an invariant based off of that. So the epsilon multiplicity is a little weird, and it turns out that it can be an irrational number, whereas every other multiplicity in my talk is going to be a positive integer. So the next type of multiplicity that's sort of related to the epsilon is called the J multiplicity. And for the J multiplicity, we looked at a filtration of the power of the ideals, and then we measured the length of the local cohomology of the quotients in this filtration. And whoops, sorry. So it turns out that this length function actually does have polynomial behavior. Okay, so that's all I want to say about the epsilon and J. So the main topic of my talk is based on Lech's inequality. So as we've seen on like the third or fourth slide or so, there are certain interaction between the multiplicity and the colength, and equality of multiplicity and colength for different ideals characterizes certain properties about R. So we're interested in the relationship between these two objects. So in the 60s, Lech didn't give a direct relationship, but he gave an upper bound for the multiplicity of an ideal I. And the multiplicity is bounded above by d factorial times the colength times the multiplicity of the ring. Okay, so in general, this bound is not sharp. So just to look at a silly case, when I is the maximal ideal, and again, a reminder, the multiplicity of the maximal ideal is the multiplicity of the ring. So we can cancel those two terms from the left and right hand side, and we get 1 is less than or equal to d factorial, and that's kind of awful. So the d factorial term is what makes this bound kind of bad. Okay, so to look at a less silly example, let's assume our ring is very local. And again, as a reminder, for regular local rings, the multiplicity of the maximal ideal is equal to 1. So we're gonna look at the multiplicity of powers of the maximal ideal, and that's just gonna be equal to n to the d. So on the right-hand side of the bound is this d factorial times the colength term. And that's going to be equal to this polynomial function in n. And just notice that this polynomial function has order n to the d. So when n is large, it's not too far off from the multiplicity of m to the n. So, so this example here led to a question by Huneke-Smirnov-Validashti. So if we define a numerical function based on this computation here, so they asked if when we plug in the dth root of the multiplicity of I into this numerical function, whether or not this is bounded above by the quantity in Lech's bound. So it turns out that if this bound is true, then based on the calculation above, it's going to be sharp when R is regular local. So again, we're going to take I to be the power of the maximal ideal. And here's just some calculation to show that we get equality. So we're going to plug in I equals m to the n. So now the multiplicity of m to the n is equal to n to the d times the multiplicity of m. And because the ring is regular, e to the m is 1. So that goes away. And we just get n to the d to the 1 over d, which exactly is just n. So we recover p of n. And based on the calculation above, p of n is exactly d factorial times the colength of the power of the maximal ideal. So the bound is sharp, if it's true. So Huneke-Smirnov-Validashti were only able to prove this bound for rings of dimension less than or equal to 3. So this question is still open as of now. Okay, but in their investigation of this question, they managed to give an improvement on Lech's bound, and it only works for rings of dimension at least 4. So they were able to bound the multiplicity of the maximal ideal times any given ideal I. And this is indeed an improvement because m times I is a smaller ideal than I, so its multiplicity is bigger. So the multiplicity of I is less than or equal to multiplicity of m times I, which is less than or equal to this Lech number here, d factorial times the colength times the multiplicity of R. Okay, so I just want to point out that when the dimension of the ring is too small, it's just false. And the counterexample is when I is equal to the maximum ideal. So the multiplicity of m squared is 2 to the d times the multiplicity of m. So then we have to compare 2 to the d with d factorial. And when d is strictly smaller than 4, 2 to the d is bigger than d factorial. Okay, so here's the main result by me and Kelsey. So we're able to generalize the improved Lech bound to both of the multiplicities that I mentioned, so to the mixed multiplicity and to the Buchsbaum-Rim multiplicity. And this is indeed, and we recover the original improved bound. So for the mixed multiplicity, we recover it when all of the ideals are the same. So when I1 equals I2 equals ID, then the right-hand side, we get the sum of the colength of these ideals, which are all the same. And so we have d many, and so we have d factorial on the right-hand side. So yeah, d minus 1 factorial times d. So we get d factorial on the right-hand side. So then for the Buchsbaum-Rim multiplicity, we recover the original inequality by setting little r equal to 1. Okay, so it turns out that based on the formula that I showed earlier that relates the Buchsbaum-Rim multiplicity with mixed multiplicity, the second inequality actually follows from the first inequality. So I'm just going to talk about the first inequality for the rest of this talk. Okay, so for the remainder of my talk, I just want to talk about the proof a bit, and then also talk about the techniques in the proof. So there's 3 major steps in the proof. The first step is to reduce to the polynomial ring case. And then once we're in the polynomial ring case, we can induct on colength and dimension. And lastly, in the base case of the induction, which is the hardest step, we need to reduce to the low dimensional cases and prove a separate bound for those cases. Okay, so let's first talk about the reduction to the polynomial ring case. So Lech type bounds have this very amazing property that says that if we're able to prove a bound for monomial ideas in polynomial rings, then that in fact implies the general bound for any ideal in any ring, which is kind of amazing because monomial ideals are very special type of ideals in very special type of rings. So here's a sketch of the reduction steps. So this was first done by Lech in his original paper, but Huneke-Smirnov-Validashti, they phrased it in a more modern term, and I'm gonna show what they did here. So we can first pass from R to the associate graded ring, and this effectively reduces us to the graded case. Okay, and then when we're in the graded case, we can pass to a Noetherian normalization S, and the Noetherian normalization is going to be a polynomial ring. So this is a reduction to the polynomial ring case. And then finally, once we're in the polynomial ring case, we can pass from I to the initial ideal of I, and this reduces us to the monomial ideal case. So there's some details that I omitted here, which is so we have to check that the inequalities involved in our inequality. So the quantities that we're concerned with is the multiplicity of the rings, colength, and the multiplicity of the ideal. We have to check that they change in a certain direction that allows us to lift the bounds from one ring to the other. And in all of the reduction steps, they do change in the right way. So me and Kelsey were able to extend the above steps to mixed multiplicity and to the Buchsbaum-Rim multiplicity. Okay, so once we reduce to the polynomial ring case, the next step is to induct on colength and dimension. And here's a key lemma that allows us to do it. So if we take an element outside of I that's a non-zero divisor and form J, which is going to be I colon X, then we have the following 2 properties. So the colength of I is going to be equal to the colength of J plus the colength of I in the quotient ring. And then second, the multiplicity of I is bounded above by the sum of these two other multiplicities. So this lemma is actually a pretty strong tool for induction on both colength and dimension. And in the special case where the polynomial R is a polynomial ring, we can take X to be a general linear element, then R prime is still a polynomial ring, but now in one less dimension, and the colength of J drops. I just want to remark that this lemma is true for any Noetherian local ring, but it's particularly useful when R is a polynomial ring. Okay, so just to show the power of this lemma, so here's a proof of Lech's original inequality using the lemma. Okay, so again, we're going to just reduce the polynomial ring case. So we're going to do double induction on dimension colength. So the base cases are easy. For the induction step, we're going to take element outside of I to be a general linear element, and then form this colon ideal as in the lemma. So then from the second part of the lemma, we know that the multiplicity of I is bounded above by the sum of these two other multiplicities. And by induction on the colength of J drops. So the multiplicity of J is less than or equal to d factorial times the colength of J. And then I prime lives in a ring R prime, which is of dimension 1 less than R. So we can use the induction on dimension to bound the multiplicity of E of I prime. Okay, so then we're going to use the first part of the lemma here, and the colength of J and I prime add up correctly. So we get d factorial times the colength of I. So this is a quick and dirty proof of Lech's original inequality that uses the key lemma. And basically the steps in this proof is essentially what we also do for mixed multiplicity and Buchsbaum-Rim multiplicity. Okay, so now let's just go back to the proof of our inequalities. But before we proceed, I just want to talk about some of the tools that we use. So here are these key tools that we use. So the first is lemma by Ries, which says that if we have the many ideals and an extra ideal J, then if we multiply the first ideal by J, we can break apart that multiplicity as these two other multiplicities here. So it's sort of like a log function in terms of the ideal. So when we multiply the ideals, it breaks apart as a sum of the multiplicities. Okay, and then the next tool that we use is a theorem by Tessier. If we go modulo a general element, then it doesn't change the multiplicity. Okay, so let's get back to our result here. So we're aiming to prove this bound here. So the multiplicity, we're trying to prove that mixed multiplicity is bounded above by e minus 1 factorial times the colength. And there should be a multiplicity of R term here, but because we're in a polynomial ring, that's just 1, so that just goes away. So to simplify notation, I'm going to denote the bound on the right-hand side by this B. So we can always assume that our ideals are integrally close, because if we pass through integral closure, it doesn't change the multiplicity. Okay, so now we're going to proceed by induction on the dimension of the ring. Base case is d equals 4, because remember, this inequality is false when d is strictly less than 4. So the base case is the hardest part, and we're just going to assume that it holds for now, and we're going to show it later. So for the inductive step on dimension, we're going to then induct on colength. So the base case for the colength is when all of the ideas are m. And so in this case, the mixed multiplicity is just 2 to the d. And we know that 2 to the d is strictly less than b factorial when d is at least 4. So the key lemma actually completes the induction step for both colength and dimension. So we're done there. Okay, so now it remains to show the base case for the induction on the dimension, which is when d equals 4. Okay, so in the base case for dimension, we're going to again induct on the colength. We're going to choose these general elements, x, y, and z, and we're going to denote by these primes to be images in the quotient rings. Okay, So we're going to use this this one property of mixed multiplicity. Again, it's the property where we can split the mixed multiplicity when we multiply two ideals together. So let's look at the mixed multiplicity that we want to bound. So the mixed multiplicity of m times the ideals. And we're going to iteratively use the above property to split the mixed multiplicity as a sum of these terms, where the maximum ideal shows up a certain amount of times with the other ideals. Okay, so then using the Tessi's result, if we go modulo these general linear elements, it doesn't change the mixed multiplicities. So we have, so the multiplicity of m times the ideal is equal to the multiplicity of the ideals plus the multiplicity of the ideals in these lower dimensional rings. Okay, so I'm going to group up all of the terms in the lower dimension as an error term. Okay, so to proceed, so just as in the lemma by Huneke-Smirnov-Validashti, we're going to set j sub I to be I sub I colon x. And it turns out that the maximum ideal of j sub I is contained inside I sub I. So this has the effect of raising the mixed multiplicity. Okay, so again, from the previous slide, the mixed multiplicity of m times the ideal is equal to the multiplicity of the ideal plus these error terms. And then the multiplicity of these ideals is bounded above by the multiplicity of m times the j ideals. And so by induction on colength, so remember the colength of j is smaller, strictly smaller than the colength of I. The multiplicity of m times these j ideals is bounded above by our bound based on the j's. But we still have this error term that we have to deal with. So to finish the proof, we just have to show that the error term is bounded above by the difference between the bounds of I and the bound based on j. And just through calculation, the difference of these bounds is exactly 6 times the sum of the colength of the I prime ideals. And this is using the lemma by Huneke-Smirnov-Validashti. Okay, so just to write out what the error term is again, the error term is just the sum of these mixed multiplicities. And so it remains to show that the sum of these mixed multiplicities is less than or equal to 6 times the sum of the colength. And it turns out that this bound is a technical result in dimension 3, which I won't show here, but that completes the proof. Okay, but I think that's the end of my talk. So thank you. This might have been too short of a talk, but yeah, that's it. Thank you for coming.
Thanks, Vinh, for the talk. Questions?
I hope I didn't go too fast.
I'm curious in the reduction to the monomial ideal case. Did you use a specific term order or?
The term order doesn't matter. So
Okay.
regardless of the term order, the multiplicity will increase, and that's all we care about.
You
So
know,
the multiplicity of I compared with the multiplicity of the initial ideal, the multiplicity of I is going to be smaller than the multiplicity of the initial ideal in any term order.
does any term order give you more information?
No.
Thomas?
It was a little fast. I was hoping you put his main result back on the screen for me.
I'm sorry that went a bit fast. When I practiced, it was about 40 minutes, but I think I went fast.
Oh, it's okay.
So how do you go by page? Is there a way to click by slides? Nope, that goes to the beginning. Main results here.
We can't see the, you're not sharing.
Oh, I haven't shared the screen, sorry. Share screen. Okay.
Mixed multiplicity. Buchsbaum-Rim Multiplicity. Okay. Awesome. Thank you.
Yeah.
I'm on your website. This is I'm looking at your CV. This is your proceedings paper. Is that correct?
Yes.
Awesome.
Right.
Perfect. Thank you. Thank you for this.
Yeah. Yeah, I should have mentioned that, but
Yeah, the paper looks really nice.
yeah, thank you.
Awesome.
Any other questions? Okay, let's thank Vinh again.